All right. Hello, good afternoon, happy Monday, and welcome to today's session. Now, I know this week you'll be hearing from a lot of AWS speakers, and so what we wanted to do with this session is bring along a few of our incredible customers and have them talk a little bit about how they're innovating with AWS and AWS storage. Now, my name is Andrew Kutze. I'm a product manager with Amazon S3, and you should think about me as your host for today. I'll be joined today on stage by Josh Smith from Canva, Bar Fingerman from Bria AI, and then Nova Desarma from Anthropic. And I'm personally incredibly excited for today's session because we'll talk a lot about data and how it's being used to drive innovation. Now, we're going to focus on three things, or themes, if you will, that customers are tackling and are really prevalent in almost every single conversation that I have with customers today. And then excitingly, you'll hear from Canva, from Bria, and from Anthropic about how they're evolving in these areas and why these are areas of importance for their business. And so we'll talk about the importance of data quality and some of the patterns that have emerged over the last year for curating really high quality data sets over really massive amounts of raw aggregated data. We'll talk about how you drive as much performance as possible from your storage to take advantage of your compute. And then as you build for immense scale, what are some of the things that you should be thinking about and doing now so that you're able to elastically scale with the needs of your business over time? Now, I know I'm the only thing that's standing between you and these three incredible customer speakers, but I do just want to start with a bit of a mental model on how I think about this stuff. And so let me jump right in with something that I think we may all be struggling with, which is dealing with massive amounts of raw aggregated data, and it's everything from sales transactions to customer interactions to IoT streams to catalogs of images. And often your teams and your organization don't actually need all this data to answer a business question, solve an analytical problem, or to find the right data to fine-tune a machine learning model. And often what they need is a clean and a really focused view of that data. And this is where the idea of data curation comes in. It's building and decorating more specialized sets of data for a particular task. And this week, you'll hear about things like data products, which is treating data as a product in the same way that you would treat other products in your organization. And so instead of one-off usage of this massive amount of data, what you're doing is you're building purposefully curated collections of data, and they're there for a very particular task, like a product manager who is trying to answer a question about how a feature is being adopted, or an ML researcher who's trying to find the right data for a particular model training task. And so today you'll hear about how this works in practice, and then some really practical tips from Canva, Bria, and Anthropic as they've made their massive collections of data a lot more usable and a lot more accessible to their researchers. Now, when it comes to performance, customers tend to think about this in the context of being able to elastically scale to really, really large amounts of aggregated throughput. And so regardless of where your compute is sitting, the pattern that most customers are optimizing for is how do you saturate the available bandwidth that exists between your storage, like Amazon S3 or our AWS file services, and their compute. And so for a lot of our customers, storage actually ends up being a pretty small portion of their overall bill, right? If you think about it, for a machine learning training workload, that bill is likely driven by GPU spend. Now, all that said and done, the thing that's important to know here is that if there's a bottleneck in your storage performance, it means that your entire end-to-end workload is stalled and it's taking longer to complete. And so your compute ends up sitting idle, and this just increases the largest portion of your bill. Now, in the context of S3, there's really three fundamental things that you should be thinking about and that we'll talk about today. It's optimizing request rate performance. So how many requests can you make per second or unit of time? Per request throughput. So for every one of those requests, how many bytes are you moving per second? And then first byte latency. So for every request, how much time are you waiting for the first byte to make it back to the client? Now, there's a lot you can do here in terms of optimizing across these characteristics. And we'll talk again about a few of them in the session. But performance is also a really, really deep subject. And so I'd recommend attending this session on optimizing storage performance with Amazon S3. It's on Thursday. You can scan this QR code to learn a little bit more. Now, let me touch on one final point, scale. And this is really just the natural evolution of everything else that we've talked about. Your applications, they're going to scale. Now, an area of relentless focus for our teams is making sure that our storage services just work. And that when it comes time to scaling from hundreds of objects to millions or billions of objects, you're not actually spending a bunch of time thinking about this. Now, let me give you an example with a storage class that we have in Amazon S3 called S3 Intelligent Tiering. S3 Intelligent Tiering moves your data between access tiers based on the changing access patterns of your data. It's automatically optimizing your costs. And so you don't have to manually optimize or worry about trade-offs between cost on one hand and performance on the other as you scale your workloads from gigabytes to terabytes of data. Now, here to talk about how they curate and how they build for scale, I'd like to invite Josh Smith to the stage.
Don't clap too loudly, folks. It is 4 o'clock on a Monday, so thank you all for being here. My name is Josh Smith. I'm an engineering manager here at Canva, and I look after a team called the Core Data team, so we naturally care a lot about all things data. And today I'm actually going to dive into some kind of interesting topics around trust and safety. So for those who haven't seen Canva before, it is a collaborative online visual design tool. You can design, upload, and create pretty much anything that you want using your own content. I will take a small jab at PowerPoint and say it is significantly better than PowerPoint for doing presentations, and I am sad to have to use PowerPoint tonight. But it's a tool that people can use to design anything. And the key thing I want to stress is that it is really people using their content, their things that they upload, and making their own sort of creations with Canva.com. As part of that, we've been on a mission recently, like a lot of companies, to try and bring AI to the forefront of everything we do. Internally, we sort of refer to it as AI everywhere. And as part of our stack, we actually have over 120 based ML microservices. So it's really sort of coming to the forefront of everything we do. So Canva has actually only been around for a really short period of time. We started back in 2012, and from very humble beginnings, we have very much skyrocketed up to over 200 million monthly active users at the moment. And those 200 million monthly active users have created over 30 billion designs, like the designs I showed on the slide just before. And that explosion of users and that explosion of the things that they're doing has really led to an explosion of content. And currently we store over 300 petabytes of data in S3. And you can imagine that there's no shortage of fun engineering problems that have sort of come along with that. So one of the things that you might sort of ask, and I need to press bigger, is that we're a company, we want to do cool AI things, and we've got this mountain of user content, so surely we can just do ML things with that, right? And the answer, like most fun things in engineering, is that unfortunately it is not quite that simple. And we really want to ensure that we have trustworthy and safe systems around how we use that data. So coming back to our users, right? Like, we really need to think about how out of that 200 million monthly active users, there is a whole bunch of different people who are using Canva.com, right? We have solo content creators, we have not-for-profits, we have educational institutions, we have large enterprises, and we have all matter in between. And one of the questions that we really want to ask ourselves is, how do we ensure a safe platform for all of these people? So one of the first problems that we run into when we start talking about safety is content moderation, right? Not all of the content that is uploaded to Canva is the kind that we want on our site, right? You can see maybe the slightly fun photo of my dog there rolling upside down is a little tongue-in-cheek, but it's indicative of the kinds of things that we perhaps, not that photo, but the not safe for work sort of logo in general, of the kinds of content that we don't want on our site. And if we don't take steps to do something about that, that can present some quite serious issues. And when it comes to AI, the thing I'd really like to stress to everyone is to consider the impact that if this kind of content goes unmoderated, what happens when that is then used as training data, which then goes into ML models, which produce potentially very unsavory results, right? And it's not just not safe for work content that I'm talking about here, it's all kinds of things when it comes to hate speech, misinformation, fraud even, and things like that. So really consider the impact of what this can do if left unmoderated. So to solve this, or to try and solve this, we've really tried to, rather than sort of getting every team to figure out how the hell they're going to do content moderation, we've built out a central moderation platform for all of Canva's services that they can hook into. So you can sort of see a rough architecture diagram there where this is done asynchronously rather than synchronously, right? Where we sort of, as new content is coming in, we're putting that on a queue. We're having workers that process those. And essentially what we do is we run a series of different models over that content, right? Where those models are able to tell us with some degree of confidence, right? Is this content safe? Is it not safe? Does it require a human moderator to sort of step in and take a look at? One of the AWS services that we leverage quite heavily as part of that for the not safe work example is Amazon Recognition. And we actually run about 70 million content checks per day through Recognition alone, just to sort of give an indication of the scale. So the thing to stress here, though, is that models can only really give us a confidence level. They can't give us a guarantee, right? There is no 100% yes, this is good, yes, this is bad. And so we do sometimes need like human moderators to step in. Another thing that sort of comes up is that oftentimes the models only sort of pick up what you've told them to pick up or what they know to pick up, right? And so we often find that users report suspicious content to us directly, and oftentimes there's clusters of the same suspicious content, right? It's not just one thing that's sort of bad, but a whole range of quite similar things that maybe all need to be investigated. So we actually have a bunch of in-house tooling for this review and flagging of content. And what's really cool on the screen you can see there is we've actually built out a really cool system for flagging similar content, right? So if we find one piece of material that we think should be perhaps not be on the site, we can find clusters of things that look quite similar. So how does that work? That's kind of a cool thing. So take these two images of my other dog, Max. You might notice that they are the same image, right? But the difference is that the photo of Max on the right has a little green dot on his nose, right? It is basically the same to us, but unfortunately, to a machine, if you take just say the raw content hash, right, of those two pieces of content, you will get wildly different hashes depending on, well, wildly different hashes just in general, right? Because as a consequence of sort of how hashes work, slight changes in the input will give you drastically different outputs. So if we want to flag similar content or the same thing, this MD5 hashing is not really the way to go. So we actually use another algorithm which is called perceptual hashing, right? And perceptual hashing is kind of cool. Don't really have time to explain the algorithm now, but effectively it looks for visually similar things. So you can see that between those two images, there's actually only a really small difference in the hash, right? And in particular, I'd call out the two green characters, right? So you can see that there is a difference of essentially 2, or like a distance of 2 characters between those two hashes. And when that distance, or the number of characters that is different, is small, we can sort of say with high confidence that that's, you know, a thing we want to flag. So that's cool and all, but how do we make that work at scale, right? And so one of the things that we've actually built out for how we run this at scale is a kind of cool algorithm that works on top of DynamoDB. It's published research that has sort of come up. And what we can do is we can say that if, let's say we set a threshold of like 3 characters difference is sort of like, that's our threshold for similar images. What we can do is we can chunk up that hash into segments. So if we're looking for, like say 4 segments, will mean that we can guarantee that we will find every result where there is only 3 characters difference. It's a math principle called the pigeonhole principle, for anyone who's interested. It guarantees that there will always be at least one exact match. And so what we do is we store all of these chunks in DynamoDB for both like images we've already processed and new ones that are coming in. And we know that if we find an exact match, right, for any of these chunks, that's a similar image. And the nice thing about that is we can implement that just using a get item call on DynamoDB. So it is really performant, really efficient. The challenge, the sort of tuning parameter of this is how many chunks you have, right? Because if you have more chunks, you need to do more Dynamo queries. And there's sort of a tuning that goes on there, which was one of the things that sort of happened when we first launched this service. We had too many chunks, and so we threw a lot too many queries at DynamoDB and sort of had to, think maybe we want to go for a smaller number of chunks. So let's sort of step back from that example now. We talked a bit about safety, and so now I want to talk about trust, right? Trust is quite an interesting concept where all of those users are storing their data with us, and so we want to make sure that they trust that we are doing the right thing with it, right? How do we make sure that that's the case? So at Canva, our stance is that we are not going to do anything that our users aren't comfortable with, and we really want to empower all of those users, right, to make their own decisions about what they consent to and about what we do with their data. And we feel that this is really crucial in maintaining their trust with us as a platform, right? In making sure that they feel that they have a say and we're respecting that say. It's also really important because it's not just what our users say, right? It's also about from a legislative perspective, right? Like people would have heard of GDPR, they maybe would have heard of COPPA, for example, is like the regulations around how you can process children's data is a use case that we come up to quite regularly, and many, many more, right? There's an ever-growing amount of regulation that dictates what we can and can't do. And so we need to make sure that we respect legislation and we respect what our users want us to be able to do with their data. So other problem that we run into is data scientists don't necessarily want to get bogged down in all of that, right? Like, that's complicated. Legal stuff is hard. Thinking about how do we respect every single user's privacy preferences is difficult, and we really want our data scientists to be focused on building, the ML things that we have really brought them on board to do, right? And making sure we're getting their time being used as effectively as they can. So one of the ways that we do this is through platforms, right? We've got another service I'm going to talk about, which is called the ML Dataset service, where when a Canva data scientist sort of needs a data set, right, this user content that we've talked about, right, they come to the ML Dataset service, they tell us the kinds of users that they're looking for, some parameters around, what they're sort of looking for as part of their experiment. And so they make that request to the service, right? Similar to before, this is all sort of done asynchronously, gets picked up by a worker. And it fans out to a service that we call the privacy preference service, right? And this service is where a lot of those regulatory and privacy consent sort of settings are stored, right? So it's actually responsible for some like 500 or so different legal rules around how data can and can't be processed. It notably includes a few things like marketing, like whether we can send marketing material to people. So this is just one of the flows where this service is used, and kind of tongue-in-cheek, the most popular one is just telling marketing that they can't spam people with emails. So it's really quite crucial for keeping track of those privacy preferences. And so what it will do is it'll return the list of users, right, that actually meet the sort of parameters that the data scientist has passed in, and who consent to the data being used, and who we can legally do that. From there, what we actually do is we federate out, right? So we actually, not all of the data is stored by these things. We have a bunch of sort of source services. And we tend to name these things around the kinds of content that they're storing. So we have the media service, the video service, document service, and so on. So sort of federate out to all of the source material, right? And then that is all batched up by this ML Dataset service into an S3 bucket, right? Where all of that content is able to be used. The nice thing about this is that the bucket that this is sort of put into, we're able to actually make sure that data refreshes, right? So if people's privacy preferences change, or even how legislation changes, we can make sure that the data that's in these things is actually being kept up to date. It's being, it's useful, right? And our data scientist sort of on the left hasn't really had to worry about any of that. right? They're able to just focus on doing cool ML things. As far as they're concerned, they've just given a list to this service, and it's given them back a data set, right? And we've been able to sort of handle all of this for them. So some takeaways from this, right? Sort of two key themes from this talk, right, is really to think about, before you even get to training, and the other two speakers will talk a lot about training if that's the kind of stuff you're into, so look forward to that. Really think about how you're processing data and what kinds of stuff is going into your systems before you even get to training. Can you handle data in the ways that you maybe want? And the second is that Canva's invested quite heavily in platforms, right? We talk about the moderation platform, we talk about the ML dataset sort of platform, right? When you invest in these things, it helps because it's able to accelerate the efforts of your data scientists. They're able to do the right thing without even really sort of trying. So that's all from me, folks. I will hand to Andrew.
All right. Thank you, Josh.
Thanks.
Now, I have the pleasure of actually asking a question. Like I listen to the session and I come up with something that I think I'm very interested in, and then hopefully everyone else is interested as well. So at the end, you were talking about like different data sets that your scientists and your researchers will be using, and you talked a little bit about the privacy preference data set. What other data sets are a part of this training workflow? Can you talk a little bit about that?
Yeah, so the data that I sort of talked about at the end, that's really like unstructured user content, like the raw things that people are sort of uploading. But we also do have a whole bunch of other sort of stuff that we work with. One of the really big ones is we have a whole bunch of analytics that sort of our product is instrumented with, how people are using the app, like, when they clicked on this thing, what sort of happens there. And so there's a significant amount of analytics events that our data scientists also have access to. We also replicate a whole bunch of structured data from other sources, so we can cross-reference things about users around, maybe whether they're on a certain subscription plan or things like that. So yeah, it's one part of sort of the data ecosystem, but definitely a quite important one.
Awesome. Thanks, Josh.
Thanks. Oh, there's no stairs there.
All right, now I would love to invite Bar Fingerman from Bria AI.
Hello, everyone. My name is Bar. I work at Bria. I'm heading the engineering. And what it means is that we're a group of people responsible for the core technology and infrastructure that enable us to train a foundation model in the visual domain from scratch. So briefly about Bria, what we're doing, we are a generative AI platform for developers, and we're in the visual domain, meaning that we're training a lot of foundation model from scratch. And our unique angle to the issue is that the fact that we're trained on a fully licensed data, meaning that we partnered with a lot of data providers that brought us the data, and then we train the model, and eventually we know how to attribute back to the data providers about the generate images and give them royalties back. And the products that we developed are three main core products that we developed. One of them is the foundation model that we give as a licensed open source, meaning that we provide the source codes and weights for a data science and research team to take and to fine-tune, to develop themselves. Again, the full source codes and the weights are available. And another tier that we have is we support APIs. So we take the models that we developed and wrapping them in APIs and expose them as a REST APIs to customers. So these are like pipelines for removing a background, replacing a background, erasing object, and a lot of variation of visual generative AI, and also in the video domain and also in the images domain that we give as APIs. And another solution is ability to tailor generation. So if you have your own brand and your own ID, we can take this data and customize the entire generation, the entire suites, according to your brand and your style. So this is today, but a while back we figured out that we had a challenge that we need to tackle, and internally we call it the foundation model machine. So we had like petabytes of data when we first started, and we had the challenge that we need to create some sort of machine that digests this huge amount of data and eventually yielding a lot of models. So today we have around 50 models. Foundation models, also auxiliary models as control nets, adapters, and so on. and we have to build that machine. So fast forwarding today, I'm going to walk you through on the data journey and the infrastructure that we build in order to achieve the ability to train these models from scratch. So as I mentioned, it's all started on the data providers. So we partner with a lot of giants that are working in this industry for a bunch of years. So Getty and Vato, Alamy, just a quick sneak peek from the data partners. And when we take this data into the system, we first digest it via data pipelines. So we work very hard to create automatic data pipelines with proprietary algorithms to digest this raw data into our system. Later on, these pipelines producing actual data that we insert into the catalog, what we call the catalog, which is a tabular way for us to categorize the entire insights that we take from the data. And from there on, we're moving to our supercomputers. So we're taking, like at peak time, 256 NVIDIA H100s and bind them all together with a high throughput bandwidth connection and train the models for 2 weeks, sometimes months of training for a single model. So it's a very heavy lifting operation on petabytes of data. After that, we're moving to an inference service that we offer, so we can run the models on your infrastructure, or you can use our inference capabilities. And later on, as I mentioned, we have the attribution engine, which for each generation know how to trace back to the original data sets that we got from the data providers and give the proper attribution per generation, per customer. So this is like a cycle that is going on that give incentive to the data partners, keep providing us data, clean and safe, and for us to train the models and give the attribution back. So it's like a value chain that we're doing across the board. So let's deep dive a bit more in depth to each one of the sections. So first of all, working with data partners, it's a pretty much good baseline to start with. We found that at least 50 to 60% of the time, developers, Gen AI developers, are spending on content moderation. They are spending the time of curating the data beforehand, dealing with hallucinations and uncertainties, and even sometimes doing post-processing in order to prevent the model to generate stuff, so it can be pre-processing or post-processing, and it's a lot of time. So working with data partners that doesn't have profanity, trademarks, and in the data set inherently, it's very, very convenient, and again, it's a good baseline. For just a quick example, here is me trying to generate in the system with our latest text-to-image model a Nike shoe, and I got the shoe, but the model perceptually doesn't know what is a Nike. He never saw the brand Nike, and he will never know how to generate that. So it's just an example that I just got a random shoe without the Nike branding whatsoever. But then we had to scale that. The model itself, when it's training, it needs to have much more than good quality data to get started with. So next challenge that we had is to build the data pipelines in order to digest the data and extract insights for the model later on. So what we did, we worked with EKS and built like a data pipeline with more than 1,000 GPU, cheaper GPU than what we trained with. It's a G5 on AWS, which is NVIDIA A10 GPU. And what we're doing, we're taking all of the petabytes of the multimodality data, which is images and videos, and we use proprietary algorithms, so we can use a multimodality LLM to ask questions about the images, give me the description and all sorts of questions, and also some computer vision classifiers in order to extract data from the image. Later on, after we have all of this data, it's inserted into a catalog, which I will talk about next. And then we can have some filtering query for the training. But then we have another data pipeline that we found very useful, is the fact that once we already have these data pipelines work on a cheaper GPUs, we found that working a divide and conquer approach and doing a lot of the operation that can be done before training on the cheaper GPUs, in opposed to do it in the training time. So imagine that on the training time, the more expensive GPU had to do all of these small operations. It will cause us really, really a bad performance time. And by doing that, by doing pre-computing all the things on the cheaper GPU, we managed to get 4x cost reduction and also speed up in the training time, which is very significant when you're training on this huge amount of H100 for weeks and sometimes months. Oops, sorry. So next, after the output of these data pipelines are eventually a JSON, just an insights on all of the data pieces. So next we had the challenge of, okay, we need to categorize them and have the ability to query fast. So we have a lot of research teams that need to get subset of the data, need to understand what is in the data, even data engineering team that needs to analyze the data and maybe go to data partners with a partnership team and ask for different variety of data. So there is a lot of things that we need to do to visualize the data that we get, all of the petabytes of data. So we chose to build a data catalog with three major components. One of them is the fire hose, the second is the glue, and then antenna to do the querying stuff. So what actually been done is each JSON from the data catalog reaches the fire hose, which is pulled into the glue, which have iceberg table behind the scenes, and then we use antenna to query. So we found that using a glue and iceberg have several beneficial features for us. So what we're using is the table formatting. So sometimes we need to add rows into the table, and it's a lot of effort to manage ourselves, like updating the data, managing the data, a lot of data engineering that we save by using that feature, and we can append rows as many as we can, as we need, and the iceberg table is managing it for us. Another thing is partitioning. For fast query time, we work with a lot of small files. These JSONs is really, really small files that tell us what it is in the image, but they by themselves are very small files. So having the ability for Iceberg to compact these small files into larger files enable us to do faster querying with zero effort. It's happening behind the scenes for us, and we just making sure that the fire hose getting the JSONs and everything happen behind the scenes. And another very important feature, because we're changing algorithms, sometimes we update the LLM, sometimes we tweak the classifiers, sometimes there is version that breaks something. Some of the classification are not good enough, and then we need to roll back. And rolling back like millions of records, it's pretty hard to manage yourself. So using Iceberg and Glue really help us with that. So here is just a sneak peek of actual usage. I just grabbed it really recently from challenges that we had. So first of all is a training subset. So for the training of an image model, one of the researchers had to have a data set with images width and height multiplication of 124 over 124, aesthetic score bigger or equal to 6, which aesthetic score is a measurement value of how aesthetic the image is. So in this case, it chose 6 and above, and a specific aspect ratio. It was very important for him to have this specific range of aspect ratios to optimize the model specifically on that. And he didn't want RGBA images, meaning transparent background images. Another example is we're using a p-hash, perceptual hash, for each of one of the images. So we're working with a lot of data partners. Sometimes inherently, some will have the data of the other one. Especially if you're working with photographers, artists, sometimes they work with several data vendors. And then remove the duplication and redundancy during the training is just a simple query, and I can find the duplicates and dispose them. And another one is for our latest video model. So we wanted to do some data engineering work and evaluate something called a motion score. When we train a video model, what's important is the peak motion, because we learn the transition function of each frame, from frame to frame. So if the video is static, it's not that significant and we don't need it. So we wanted to evaluate what is, with our eyes, what is the best motion score to train on. So we started to sample, like random sampling, 1,000 images from with buckets, like bucket 6, 6 to 10, 8 to something, and then we managed to find the ideal calibrated with our eyes and find the ideal motion score. In this case, it was 6, but this is just the query that helped us to do the data engineering work around that. So after we all said and done, and we have our subset of data, it's time to jump to the real training. So for that, as I mentioned, we're working with a huge fleet of NVIDIA H100, which is a monstrous of GPU. And we develop our algorithm, which is the training loop, to train the model. And it's an iterative process where it takes millions of iterations on, again, petabytes of data that we need to stream to the cloud for days and weeks and months. So there is a lot of optimization that we did on the compute layer, but I will focus right now only on the data part. So eventually what we came up with, the architecture of streaming the data to the cluster, is the fact that we work with, let's say, images that are very small files, 1 megabyte, 5 megabytes. It's not like huge files, and you have a bunch of them. So we found that the AWS basically is optimized for throughput, for bandwidth, and not for opening connections. So opening millions of connections to the cluster for weeks and days is like a killer. You cannot train like that. It will kill your experiment. So we experiment with some compaction parquets files. 5 gigs work best for us. We tried 5, 2, 10. We found that 5 gigs is ideal parquet size. And then we save all of these parquets in S3. And we connect to the cluster via fast file mode, which is an S3 feature with SageMaker, which is the platform we use for training jobs. And this actually gives us the ability to work in our algorithms natively. We call a file natively in the file system. And behind the scenes, AWS will stream that file on demand. So when I ask a file or a bunch of files, I work like I work on my local machine, and I get the file behind the scenes stream from S3 to the cluster. And after that, each GPU is working as a standalone unit, and each data loader that loads data from the GPU, we found it really optimized to work in a divide and conquer approach. So each GPU knows in advance the shard that is going to fetch, and it's fetching it, again, in the iterative process in advance in order to be more optimized, in opposed to each GPU to say, hey, I took shard number 1, calling the next one, get shard number 2, and so on and so on. It will be impossible to converge that way. So doing all of that enabled us to scale to 0 very easily. So there is nothing to connect to the cluster or to synchronize like external storage or pay for extra live storage to mount to the cluster. We just work with S3, which we already do, to store all the files, and we stream them to the cluster on demand. So scale to 0 is easy, and also cost-wise, because the cluster is in the same region as the storage, we don't pay for data transfer. So it's minimal cost for us. And again, working with the access pattern of each GPU working as a standalone unit, it's very, very optimized in performance. We will not be able to train models otherwise. Oops. Okay. So last piece of the puzzle is the attribution. It's an engine, as I mentioned, to give back attribution to the data partners. So for example, if I took one of our latest model, 2.3, and I generated 2 kids running in the forest, and I used the inference service and got this specific image. Now the attribution engine part is to trace back for the data part, all the data partners, and find the one that should get attributed. So here we are using the same recipe as we did with the catalog, the iceberg tables and the glue and the glue with Athena to store all the records. So if you have a hit, we store it in the catalog to get reports back to the data partners and say, yeah, you should get a cent, you should get $5, and so on and so on. So we're using the same mechanism, the same architecture exactly to handle this type of scale. And you can see this is a web application that we have to show the data partners. This is an internal view that shows us which data partners receive what. Each data partner see only his part. But in general, this is the concept. Now, the scale of the attribution, I just plotted a graph of one of our image model for the last year. So only in the last 6 months, we have a growth of 100 million rows in the attribution for a single model. And it's add up to 2 billion rows of attribution only in the last year. And again, it's only a single model that we have. We have over 50. And just for you to see that when we're going to scale 2025, we're going to be even at least 10x more. We must have to find a solution to manage the scale, the upcoming scale. So we found again that using the glue with the iceberg table really support that scale for real-time querying for this huge amount of data rows. So thank you very much. If you like to see all of our models are open, You can play with playgrounds, generate stuff, use control nets. Everything is open and available through Hugging Face. Don't take my word for it. Try it. Thank you.
All right. Thank you. Now, the thing that I took away from the talk is the use of Iceberg for the attribution, which is like really awesome. And you mentioned 2 billion records. Where do you see Bria going in the next year?
Yeah. So let's take the simple unit of economic maybe. Let's take one customer that do inferences and one data provider. So let's say if you're doing one inference, it might be for this specific data provider, 10 images will be returned because 10 images for this data partner really help to compose the pixels of the generated images. So looking at the simplest one inference multiplied by 10. Looking at multiple customers, multiple data providers, the multiplication here are huge. Like one customer can do 100 million generation per month. And again, multiplied by the data partners and the number of attributed images, it's a big multiplication. So we see the scale exponentially growing on each onboarded new customer that is doing inference. So it's like endless scale eventually. So we had to work something out to handle this scale.
Awesome. Thank you, Bar.
Thank you.
All right, next I'd like to invite Nova Desarma from Anthropic.
So hey everyone, Nova from Anthropic. For those who might know us, we're the AI research and safety company behind Claude, our AI assistant. Today I'm thrilled to dive into how Amazon S3 has revolutionized our data processing capabilities, which is a lot of words to say how much S3 we use. This has been a pretty big journey. I talked about this a little bit last year, which also, if anyone's interested in that, there'll be some deltas from that today. And whether you're considering scaling your S3 usage or whether you're just curious about sort of what large-scale AI infrastructure looks like, hopefully this will provide you guys with some valuable insights here. And let's see if we can use a clicker here. So here's a scale slide. I was going to put one half on and then the other half, but they're both big numbers, so you can look at them both at the same time. So previously, for our older models, we do a lot of data deduplication, as like other folks have talked about today. But to kind of give you a sense of the scale that we're operating at, we're processing data sets of like 200 petabytes every 2 weeks, which, just to put that in perspective, that's like 230 miles of DVDs sort of stacked up or something like that. And we struggled to sort of like get to that scale for a bunch of different reasons, one of which is that we're kind of uncompromising on the way that we do this. There's a lot of ways that you can sort of shard your data. There's a lot of ways you can sort of like make sort of sacrifices in the name of efficiency there, and we weren't willing to do that. So getting it this high has been a process. Previously, we were doing 4 to 5 day dedupes, so like these 1 week cycles. And this is very difficult to work with for researchers. Researchers want to be able to do this all the time. And so through a whole bunch of optimization, we're now handling these 200 petabyte data sets that are 200 times bigger in 1 or 2 days. And so let's talk a little bit about how we got there. We've talked about a bunch of different services today. We love S3. 3 different things that we use for our sort of high-performance, IOPS-intensive operations, things like shuffles and more shuffles. S3 Express One Zone has made that possible for us. Rather than using Hadoop or EBS or EFS or many other kinds of like shared file systems, we like to stay inside of like S3 for this. S3 Express One Zone lets us do as many IOPS as we want to on that data as quickly as we need it for a shuffle. So we don't need to have that big disk in the back. For multi-reader sort of bandwidth-intensive operations, we use cross-bucket replication. So that way we can store our data in the same place that our compute is, but we don't necessarily have to process it there. We use GPUs, we use other accelerators, and we want to make sure that our data is co-located there, but when you're doing a shuffle that big, or if you're doing a filter that big, you may not be able to be in the same region. So cross-bucket replication has been helpful. We also use gateway endpoints there to try and keep the cost down, because if you are using a gateway endpoint, you save dollars on transfer costs. And finally, S3 intelligent tiering has been crucial for sort of managing those costs as we scale. We train language models. Our language model checkpoints are enormous and also very rarely accessed. So it will be very expensive for us if we can't go back to one of them, but like 90+% of them are never touched again. So intelligent tiering is a very good option for that because it automatically tiers things down for you. And let's talk about those model checkpoints a little bit more. One of our sort of key optimizations here was designing our S3 structure for model checkpoints to be both easy for users, but also easy for S3. So S3 loves prefixes and sharding across multiple prefixes, and users like file systems. So that is it's not a great match in some ways here. So one of the things that we did is we took our metadata out and gave it a sort of like standard file system looking structure because the metadata ops aren't as significant. And then the checkpoints themselves are in a sort of reversed key structure here. So we say like run type, which is like maybe it's like an SL or an RL run, so like supervised or like reinforcement learning. And then there's like a run name and a checkpoint type, so it's permanent or periodic or ephemeral. And then some kind of checkpoint number, which is saying like this is the first checkpoint, this is the 10,000 tokens, this is the 10 billion tokens, this is 10 trillion tokens checkpoint. And we have this throughput optimized structure here that we use to store the model itself. So we can shard it out right at the beginning of the path. That means that those prefixes will be warm because we've distributed the we've distributed the writes among multiple prefixes in that same bucket. But users are still able to ls inside of a directory and see what they want to see. This was like a pretty big impact for our workload is actually using shards effectively here, because if you look at that list objects there, that is the reverse of what you want to be doing. And sharding stuff out has like helped us avoid 503s and slowdowns and things like that, which is important when you're trying to restore a run across thousands or tens of thousands or no comment number of machines. We click. Storage elasticity. So one of the nice things about being in the cloud, TM, is that we're able to scale our IOPS up and down based on the workload. I've worked in shops that are primarily data center based, and one of the risks there is that you just didn't put enough disks in the data center, you don't have enough SSDs, you don't have enough IOPS, and to scale to the number of IOPS that we need to do, and the amount of bandwidth that we need to be able to shove through sort of these machines would involve us idling a lot of infrastructure. And one of the nice things about being on this multi-tenant infrastructure is that we're able to scale elastically, which is great for these like bursty training patterns where one of your servers dies and then you have to restore the whole checkpoint for this massive model across many, many machines simultaneously, and you want to limit the downtime as much as possible. And while there are smart ways to do that, we are actually able to do the dumb way sometimes here and just get a lot of bandwidth, which is fantastic. No need to provision for peak. There's no over-provisioning costs here, and it makes our capacity planning a lot easier. And speaking of capacity, so this is the number that I had last year. We were talking about 800 gigabytes per second with no provisioning, pre-required. And this year, we've got another number, 1,500 gigabytes per second. So we're hitting in terabytes per second of sustained egress in a single region. So this isn't counting all of our stuff, but it's a good number. So appreciate the number. It's kind of it's a big shift in sort of what we're able to achieve here. That doubling kind of that doubling gives you Sonnet 3.5, which is the best code model in the entire world. So it's worth it for us, I think. Just to put this in perspective, you could transfer this sort of Netflix catalog, which is like 3 petabytes or something like that, in under a second. It would take less than 30 seconds to transfer the entire content of the Libraries of Congress, which is 15 petabytes. Pointing at this a little bit more, modern NVMe drives can maybe give you like 7 gigabytes per second or something like that. That's a lot of drives to drive, so I'm pretty happy that someone else is doing that for me. Let's talk a little bit about something that's more concrete here. We also need to be able to, on the receiver side, be able to get that data into our workloads. We use a lot of S5 command, but we also use a lot of the AWS common runtime-based S3 client because we're using accelerated instances. This is automatic, though I think it's automatic on more machines than that. I can be corrected. This gives us better connection management. As was mentioned previously, if you have to create a new connection every single time you do anything, that's going to be expensive. Amortizing your TLS startup cost is pretty valuable. We had a lot of code to do this. CRT has replaced a lot of that code for us. And that means that we just get better throughput for large-scale operations. One other thing I wanted to note here is that we want to be able to do as much async I/O as possible, and not async I/O, but like asynchronous IOPS, where we want to be able to queue up our data ahead of time, so that way we can absorb any kind of like latency, jitter, things like that, by just having a couple of gigabytes of data sitting around in RAM. And as long as you're able to, as long as S3 is able to scale to that throughput, you can hide as much latency as you want there. So that's a convenient thing for us, and it's one of the reasons that we've stayed with S3. And let's talk about sort of like the way that this impacts our data strategy. So the biggest one is that we're able to continue to run filters on larger and larger data sets. Like I mentioned, we've scaled like maybe 200 times or something like that since the last time I gave this talk. And this gives us like the ability to do more comprehensive deduplication strategies. So I've got this great figure here with a couple of different shards of data. So you imagine that they are stored in different prefixes or something like that. One thing that you can do here is you can do like a sharded deduplication, where you look within the shard, and then maybe you go across for some percentage of that data or something like that. And one of the things that we found is that this is very hard to scale effectively, that there are like a lot of losses on the shard boundary for us, especially when we're doing things like semantic deduplication, where we've talked about perceptual hashes in the image domain, but there are similar kind of techniques that you can apply to the text domain and other kinds of domains. And semantic deduplication works a lot better with a global dedupe. As you can see, that we've deleted a lot more of that data. We have more understanding of sort of like how that is used, and that gives us a better understanding of how good the model is going to be at the end of the day, because deduplication and duplication sort of in general in your data set oftentimes results in a worse model. So being able to continue to have a global dedupe with a fast dev cycle as we scale, I'm shuddering at what this is going to be next year, has been pretty valuable for us as we continue to grow. It is expensive. So one of the things that we like S3 intelligent tiering for these automatic storage class transitions. You can see that we've got this kind of like ratio here around the different kinds of storage that we do. I gave you a slide off of our sort of CloudWatch here. We also use we use a couple of other things here for finding large prefixes for potential pruning. One of the things that we found was that someone was storing kind of there's like a dash in this graph here towards I guess it's going to be the right-hand side of the graph. You can see where we went down instead of up, which is a real change of pace for us. That was somebody storing a shuffle sort of component for a few months that they perhaps didn't need to. And I think that was something where we, looking at auditing for large prefixes here, this helped us out a lot. We also standardize our lifecycle rules across buckets, so things like expire aborted multipart, delete your past versions, move things to intelligent tiering, remove the old stuff. That's something that it's convenient to be able to do inside of Terraform, especially as we increase the number of buckets and regions. Here are a couple of lessons learned. So one of them is you should consider sort of future scalability when you design your key structures. Thinking about prefixes when you do that and implementing some kind of naming convention here means that you're going to be able to serve the needs of your users, whether those are sort of your data scientists or whoever your consumers of that data are, while still being able to get the throughput that you need. I recommend using more of the S3. S3 is like a great object store, but it's a lot more than that as well. So thinking about things like express one zone and intelligent tiering for cost management. And think about migration strategies. There's oftentimes, like when you have a bunch of data sitting in one place, it's not necessary to move all of that data at the same time. So, and I guess I'll pass this back to you.
All right.
And I'm not going to get trapped on this side of the stage. So.
All right. So thank you. What really sticks out is at your scale, your checkpoint storage. Can you talk a little bit about how you manage that? How do you prune them? How long are they kept around for?
Yeah, let's talk about checkpoints for a second. So we already talked about sort of this key structure here. We use a sort of hierarchical checkpointing system where we want to sort of erode the data over time. The likelihood that you want a particular checkpoint around is something that you can sort of treat as an exponential. And so we use S3 inventory reports to drive a process that removes checkpoints over time to sort of save on costs there. This is kind of similar to what intelligent tiering does and sort of works in concert there. But we've got these, like I mentioned, like 3 different kinds. Explicitly ephemeral ones, which are deleted after like maybe 30 days or something like that. And then periodic and permanent snapshots, which are terribly named, where a periodic snapshot is also permanent, but is stored every X number of tokens, and permanent snapshots are stored also in an exponential as like the run goes on.
Interesting. And you talked a little bit about working with a bunch of data and training with a little bit more multimodal data. How are you managing the multimodal data?
Yeah, that's interesting. I think like multimodal has been a cool data challenge for us because text is very easy to compress. Like when I look at that 200 petabyte number, that's like mostly text that we're talking about. But like for images, that's like much bigger, and it's also a lot of small files and things like that. We do a couple of different kinds of data prep. Some of it is ahead of time, and some of it is just in time. Basically, all of our multimodal stuff is just in time, so we store a very large number of files. This is sort of me talking around that we just kind of put all the image files in S3 and we kind of call it a day. And we trust the prefixes to take us where we need to go. Having async IO and having like sort of like a big throughput optimized S3 sort of stack lets us just not have to think about it that much. And this works out pretty well for most use cases. There's a sort of tragedy of dev cycles here that you do have to think about a little bit, which is that your small models oftentimes will consume more tokens faster than your big models do. So your big model can be totally fine with a certain amount of throughput, and then your small models, those are the ones that kill you, and there are so many more of them, oh my god. So that is something where we're thinking about, like, how does this scale up exactly? Depends on what your use case is, but right now it's S3 is just kind of doing its thing.
Awesome, thank you.
Thank you.
All right, I want to wrap it up by saying thank you to our speakers. We had Josh from Canva, Bar from Bria AI, and Nova Desarma from Anthropic. Thanks, everyone. Have a good rest of the week.